Hi folks, here we're going to work through an example of a question relating to gravitational fields that includes determining the position of a neutral point. So the question reads, the Earth has a mass of 6 by 10 to the power of 24 kilograms and the Moon has a mass of 7.3 by 10 to the 22 kilograms. The distance between their centres of mass is 380 megameters. The Moon's mean radius is 1,740 kilometers. So before we even look at the actual questions that were being asked, I think the first thing we'll do here is just to quickly sketch out what information we have already. So we have two objects of mass. We have the Earth and we have the Moon. We are told what the mass of the Earth is, that's 6 by 10 to the 24 kilograms, and the Moon is 7.3 by 10 to the 22 kilograms. We're also told the distance between the centres of each, and that is 380 meganewtons. So I'm going to convert that into meters, and that mega is 10 to the power of 6 meters. So, part A, calculate the gravitational force between the Earth and the Moon. So let's start off with our equation. Force is equal to the gravitational constant multiplied by mass 1, in this case that's the mass of the Earth, multiplied by mass 2, which in this case is the mass of the Moon, divided by their separation squared. So let's put in the values that we know. G is a constant, so that's 6.67 by 10 to the minus 11, multiplied by the mass of the Earth, which is 6 by 10 to the 24, multiplied by the mass of the Moon, 7.3 by 10 to the 22. And that's all divided by the separation squared. So remember that separation needs to be in meters, so we've already converted it when we added it to the diagram. And then we just need to remember to square that. So pop that number into a calculator and we get an answer of 2.02 by 10 to the 20 newtons. And I'm giving that just the three significant figures. So next we'll look at part B, calculate the gravitational field strength on the Moon's surface. So for this we will use our equation where the gravitational field strength G is equal to the universal gravitational constant, that's capital G, multiplied by the mass of the Moon divided by r squared. So the constant, which we've already used, is 6.67 by 10 to the minus 11, multiplied by the mass of the Moon, which is 7.3 by 10 to the 22 kilograms, divided by r squared. So r squared here refers to the separation from the point in question to the centre of the Moon. Since we're trying to figure out the field strength on the Moon's surface, this value r is equal to the radius of the Moon, which is 1,740 kilometers. So that's by 10 to the power of 3. So we're converting that into meters. And then that distance is also squared. Then it's a matter of popping that into a calculator, and that gives us a value of 1.61, and that is newtons per kilogram. Okay, so let's have a look at part C. At a certain point P between the Moon and the Earth, the force exerted on a mass by the Earth is numerically equal to that exerted by the Moon. Calculate the distance between the centre of the Earth and P. So somewhere in between the Earth and the Moon, there exists a point P where the gravitational field strength is 0. So that means that the Earth is pulling on an object at point P with the same force per kilogram that the moon is pulling on that same object. So what we're going to do is label a few things onto the diagram here. We're trying to find the distance between the centre of the Earth and this point P. So I'm going to label that distance as x. Now if we know that distance, or we've called that distance x, we can actually also come up with an expression for the distance between the centre of the moon and P. And that would be given by 380 by 10 to the power of 6 minus x. So this point P is what we call a neutral point. It means that the Earth is pulling on this mass with the same force as the moon is pulling on the same mass at that point. So what that means is that the gravitational field strength is 0. The resultant field strength is 0. And we can write that as the gravitational field strength due to the Earth at point P is equal to the gravitational field strength due to the moon at point P. Now remember what our equation for gravitational field strength is. It was the force per unit mass. Or we can also write that as G, the universal gravitational constant, multiplied by the mass divided by r squared. So if we take that equation and apply it to the first equation that we looked at, that is the gravitational field strength of the Earth is equal to the gravitational field strength of the moon, then our equation changes so that we have G times the mass of the Earth divided by the separation squared. Now the separation between the Earth and point P is given as x. So therefore we have in the bottom line x squared. That is equal to the gravitational field strength due to the moon. And that equation becomes G multiplied by the mass of the moon divided by its separation from P to the centre of the moon. Now that distance, which we'd labelled on our diagram, is 380 by 10 to the 6 minus x. And then don't forget that that is squared. So looking at this expression, we can see that G occurs on both sides and we can cancel that out. And we do know the values for the mass of the Earth and the mass of the moon, so we can put those in as well. So now we have an equation with only one unknown, that is x. So we want to rearrange this equation in order to find x. First, we'll need to get all the x's on the same side of the equation. So I'm going to try and get all the x's onto the left-hand side of the equation. And to do that, I'm going to bring this expression, the 380 by 10 to the 6 minus x all squared. I'm going to bring that over to the left-hand side where it becomes a multiply. So it will go up onto the top line. And at the same time, the 6 by 10 to the 24, that's the mass of the Earth, I'm going to bring it over to the right hand side where it's going to become a divide. So essentially it's just swapping places. So remember that the aim of this is to try to get x equals. So we're going to want to get rid of the squares that we have here on the left hand side. So to do that, we're going to take the square root of both sides. When we do that, we're taking the square root of the left hand side and we're taking the square root of the right hand side, which is the mass of the moon divided by the mass of the Earth. And that ends up giving us 0.11. So now we don't have any x squareds. Now we're just going to bring that x from the left hand side that's on the bottom line, we're going to bring that over to the right hand side on the top. So we're left with 380 by 10 to the 6 minus x is equal to 0.11 multiplied by x. Now I'm going to bring the minus x on the left hand side over to the right hand side where it will become a plus. And finally, to find x, we're just going to take 380 by 10 to the 6, divide that by the 1.11, and so that value works out to be 3.42 by 10 to the 8 metres. Okay, on to part D. Sketch a graph to show how the gravitational field strength varies with distance from the surface of the Earth to the surface of the Moon. Remember that the field strength changes direction at a point P. Okay, so what I'm going to do is I'm going to draw out a set of axes just below the diagram that we drew earlier. On these axes, I'm going to put R, that's the separation or distance, on the x-axis, and on the y-axis we're going to put the gravitational field strength. I'm also going to do a couple of dashed lines from the diagram just to show how they correspond to the graph. So in particular, we've got our point P here, and I'm also going to put on the surface of the Earth and the surface of the Moon. And that's just to help me visualize what's happening here. So, starting from the surface of the Earth, we know that as we get further and further away from the surface of the Earth, then the gravitational field strength will decrease. And it follows the inverse square law. So we're going to have an exponential decay curve here, starting from the surface of the Earth until it reaches point P. And as we've already discussed, at a point P, the resultant gravitational field strength is 0. So we should have a decay curve that reaches the point 0. Now, after this point, the gravitational field strength is going to start to increase again as we get closer and closer to the Moon. However, we need to take into account, first of all, that the gravitational field strength on the surface of the Moon is not as big as it is on the surface of the Earth. We know on Earth that at the surface, the value G has a value of 9.81. But we actually already calculated in part B of this question the gravitational field strength at the surface of the Moon, and that was only 1.6. So therefore, when we have this curve that starts to increase as we get closer to the surface, it's only going to go as far as 1.6. We do need to incorporate the change in direction as well. So instead of that curve going above the axis to a positive value of 1.6, it's going to go to a negative value of 1.6. So this value here is 1.6. So finally then we have part E. So using your answer to part D, suggest why it would require more fuel to travel from Earth to the Moon than to return from the Moon to the Earth. So as you can see from the graph that we labelled already, we know that the gravitational field strength at the surface of the Earth is much bigger than the gravitational field strength at the surface of the Moon. So therefore you would need more fuel to overcome that pull of gravity on the surface of the Earth than you would do on the surface of the Moon. Another thing to take into account would be the location of that neutral point P that we calculated earlier on in this question. So I'm going to redraw this diagram to show the Earth and the Moon, and this point, this neutral point P, which we determined was 342 by 10 to the 6 metres. If you remember, we had 3.42 by 10 to the 8. So we can rewrite that as 342 by 10 to the 6 metres. And that's until the neutral point P. Now that means that the Moon is only 38 by 10 to the 6 metres from that point P. So therefore it's much, much closer to the Moon than it is to the Earth. So in terms of travelling from one to the other, if we're travelling from the Earth to the Moon, then we have a much, much greater distance to travel to get to this point P, beyond which then the gravitational pull of the Moon would take over. So we need a lot of fuel to cover that really big distance here to point P, and then once we get to P we don't need fuel anymore because the gravitational pull of the moon will bring you in the rest of the way. However, for that return journey to go from the moon back to the Earth, you've got a much shorter distance to travel to get to this neutral point P, and then after that the gravitational pull of the Earth would take you in the rest of the way. So that's another thing then just to consider as well. So that's it. That's a worked example from start to finish, and hopefully you found some of that useful.